Okay, so we're going to move on to running the model. So from the break, it would appear that everyone is actually up and running. And if you aren't, I'm sorry, we can't help you now get to the point of building. That's kind of assumed you've now got the solo executable ocean only MOM6 now compiled. So we're going to move on to running. And I'm just going to quickly explain something about the context in which you're going to be running before we get down to doing a live demo on my laptop. So we're going to cover how to actually run the model, and then we're going to cover how to control the model, what the model's doing when it's running. And so that's what we're going to talk about in the next 45 minutes. So I'll be explaining what you need to do and then what you need to do to control the model. But first, I just need to explain a bit of context. So those of you who are running your laptop, you just do what I'm going to do on the screen, which is work in a single shell, and you'll be able to follow the same commands. If you're able to build and you're able to do the double gyre, run the model in ocean only double gyre that Marshall did right at the end, you're good to go, and you just do what I do. If you're running on an HPC, that means Gaia or Stellar, you have to, you already had to use different templates and configuration, the environment compatible configurations for that system. But you also need to understand how an HPC is configured. So in general, and HPCs vary, every machine is different, unfortunately. But in general, HPCs are massive machines, but when you connect to them, you always connect to what they call a login node. And that login node is not the HPC, it's just the front end. So it's a machine, as I'm kind of illustrating here, which is sitting at the front of the machine. It's connected to the internet, otherwise you wouldn't be able to reach it. And that is actually where you do all of your interactive stuff, such as running, make, and doing your compiling. There is a group of machines which are normally called the cluster or the compute nodes, and you need to reach those through some job scheduler. And the most popular one right now, everyone seems to be using it, is Slurm, and it has commands such as sbatch, sq, srun, and salloc. And those are commands which you need to use. And these instructions have been written out on the various wiki pages. I haven't got the links here, but if you had got to the point of compiling, then you should be on that wiki page already for your particular platform. And you will, on the compiling step, you've done that. Everyone uses make, we generate a make file to do the building, but you will need to move over to the compute nodes to actually run the model. Most login nodes do not have the MPI library set up to actually use MPI there. It's unfair to everybody else because those are the interactive nodes. If you start running parallel jobs there, you'll be bogging down the cores on those nodes. And the idea is the compute nodes were designed to do the parallel jobs. So you will need to get, in this, if you want to follow through live, you will need to get an interactive session, and the format is, on Slurm, you'll use salloc, which is like gets you an allocation for on the compute system, but interactively. And so it will be something of the form salloc minus nodes 1 or ntask 16 or something like that. But every HPC, unfortunately, has configured Slurm differently. So it depends on the HPC. Again, we've tried to write out the instructions specific to Stellar and Gaia on some respective pages. And then when you actually run it, instead of using MPI run, which we'll do when we're running on a laptop, you will use srun instead of MPI run. Stellar, here the specifics for Stellar, I will give you a chance just to try this. salloc, you have to have a project name. If you're on Stellar, you will presumably be in Seams2, but you may not be. You might be in another project. Here I'm specifying I want to have 8 cores, n tasks, and the -t is short for time, and it's measured in minutes, so this is for 60 minutes. So I'm just asking for an interactive session on Stellar for 60 minutes, and then the corresponding command is srun -n8 for that. Now, yes. These are not on the web. This is PowerPoint. Sorry. We will do it after retroactively. Sorry. Marshall's the modern one here. I'm old-fashioned. I know. I totally agree. I was envious. I think that's a good. We'll have to follow Marshall in the future. So where was I? Yes. So conventionally, we're going to try and do things interactively because we want to show you how things are working. You will be in trouble if you do all of your research interactively. You will be, and it's actually bad practice for you anyway, because if you lose internet connection, you lose the session. So you're supposed to actually create a batch script or a job script, we refer to them, in which has the commands that you would type out interactively with slight variations. And so, for example, this is a very simple job script I've written out that does work on Stellar for the same 8 tasks here. And you know, this is the sort of thing you have to figure out for your HPC. And this is what you will do when you're running the model in production mode for yourself doing research. You will submit jobs, and when you're doing this, you need to actually go through the exercise of figuring out how long will my job run, give yourself another 5%, and then actually figure out all the scheduling, all the details of where you want to put, which directions you want to put stuff, move stuff around, and so on. That's all contained in your job script. Now, later this afternoon, or let me just get to Gaia first. So the same commands are for Gaia here. So it's different because every HPC configures Slurm differently. So they use clusters and nodes instead of event tasks. And there's a very simple job script that does work. On Gaia, most of the sort of work you're doing will be with the GFDL models, presumably even the couple models. And for that, we have a session this afternoon that Raf's going to run, where we're using a framework, a system that actually does all of this for you called Free. And so he's going to demonstrate that. And that is the preferred way to run a GFDL sanctioned model, because it does an awful lot of stuff, including moving the data from Gaia, which is a lot down in Oak Ridge, back up to Princeton GFDL's file systems. So that's one of the main reasons why you want to use Free, but it also does a lot more stuff. It does some post-processing, organizer stuff for you. You need, if you're using GFDL models, please, pay attention to Raf's talk and figure out how to use Free. But for everyone else, you kind of have to do it yourself, because Free is specific to GFDL, and this is the sort of thing you would have to do if you're doing it there, if you're doing it yourself. Okay, the last thing I was going to say is at the make stage, Marshall showed you make repro equals 1, which is the mode in which we get reproducible results. Later on, I think it's either tomorrow morning. Yes, tomorrow morning there's going to be a debug session. You would actually replace repro equals 1 with debug equals 1, and that will actually build on a lot of debugging information into the executable, into the object files and executable, with lots of traceback, and it will not be optimized. It will be very slow. This is the way, and when you're developing, sometimes you always build in this mode just so you have a lot of information when you're trying to actually developing the model, but you can't afford to run this way. Now, when it comes to affording to run, is a hint, if you remove the repro equals 1, it goes into what we call production mode. That is not guaranteed to be reproducible bitwise through different versions of compilers and so on. Even that's hard work with repro equals 1. But the reason I mention it now is, if you're trying out the exercises with me now, you might be better off if you do a make clean in the MOM6 directory, not the FMS directory, and just do make -j without the repro equals 1, because your code will go a little about 30 or 40% faster. So I've done that already here in order to show, have the model run in live without too many delays. So we're going to switch over now to a live session. Excuse me. And I just want to say before, so I've already compiled MOM6 here following the instructions Marshall did earlier this morning. I've also installed myself a Conda environment because I need to be able to look at what I'm doing. Now, this wasn't a prerequisite for you to run the model or to understand how to run the model, but I'm needing to do it just to be able to show you some output. But again, Raf is going to give you a more comprehensive explanation about how to analyze the model later. Is that today? Today, yeah. But miniconda is how I've installed it. So there's a miniconda 3 directory and this bash script that was needed to install it. The instructions for that were at the bottom of the tutorial section of the front page MOM6 examples wiki. So in MOM6 examples wiki, I could show you that. Here we are. So in the wiki here, if you go through to tutorials, at the bottom there is just a quick cheat sheet about how to install Jupyter and the Jupyter environment using miniconda. Again, Raf's going to cover this in much more detail, but in this instructions, I've already set up an environment called MOM6Pi, and I think a few of you have already done that. I saw a few people with MOM6Pi in their shell names. So that's what I'm going to be using here when I start doing some stuff live. So that's why there is this directory in my home directory. There's a setup like this. Now I've got MOM6 compiled already. And we've already built it. So ocean only, so you'll see that all my object files are here, and I've got an executable. And so now we're going to figure out how to run that. So again, remember, you need to do, if you're on an HPC, get onto the compute nodes for the next step. So what I want to we're going to go into an experiment called ocean only Phillips 2-layer. So this configuration is actually a snapshot of the model that was used for one of the experiments in a paper by Hallberg in 2013. It's a paper we'll refer to again later when we're discussing all the parameterizations in the model. But this experiment is derived from the classic 2-layer Phillips model. And so there is a configuration of MOM6, which, as you can see here, that works in that mode. It is actually slightly, we're going to adapt it a little bit before to actually get it back into a pure Phillips mode. And then later this afternoon, we're going to adapt it even further. But I want you to go into that directory now. And if you do an ls, if you haven't run in here already, it should look like this. Let me just make sure, I don't know if on my screen, I've got a video, inside video there. So right now there's 8 files. And in fact, only 4 of those files are input files. So I just want to quickly just go through this. The model requires as input an input.nml, an input.nml file. I mean, that's kind of a bootstrapping Fortran nameless file. We'll go into that. And then the actual parameters are going to be in these mom input and mom override files. And I'll explain how we configure those. And then the other bare minimum requirement is the diag table. And that controls what diagnostics the model is going to write. So those 4 files are the actual inputs. The other 4 files here, are called, which are in the format of mom parameter doc, and then something like all or debugging or layout or short. Those are actual output of the model. And we actually, just as a matter of practice, we've developed this idea that we actually record those in experiments because these are the complete and exact state of the model in order needed to actually reproduce the model as was run. And the reason that that's powerful is, it's very easy to start, making, you can happily make an edit to a file and then forget that you made the edit and think that you've only just run the model. And you can actually look at these outputs of the model to actually know what the actual state was when you had the last output generated. And we record these in the repository because it's a very good record of the evolution of the experiment as we're developing it. Something we'll get into later today. So the first thing I want to show you is the input.nml file, because this is what's needed to bootstrap the model, and it also controls how. Can I get rid of this thing? My vision. Yeah, that's good. So the important name list is this mom input.nml at the top of this file, and it has just a few variables. These are not parameters in terms of runtime parameters that the model uses for the numerics. These are just kind of the infrastructure, the environment variables. And it tells there's actually an FMS read by FMS. We use an FMS package to read it into MOM6, and this just creates things such as tells the model where it's going to write the output, where it's going to read the input from, and so on. And in particular, we have this parameter called parameter file name, and that is just a list of other files. And by convention, we have been using mom_input and mom_override for the list, the place to put parameters. And I'll explain why we have 2 in a minute, but you might find experiments where we have 3 or even 4. And you are absolutely free to use whatever names you like here. You could say, I want to call my input parameters, my input file Fred. And all you have to do is put it there and make sure the parameters are actually in Fred, the file. So this is the bootstrapping. This is what tells mom when it's starting where to read its parameters. The other stuff is sort of technical things such as to do with the size of the stack on the computers and so on. These are things which you shouldn't have to touch, but sometimes you might get a warning message or an error message from FMS saying it's run out of memory or something, and then you would have to Google or send a message to one of the forums and ask, what do I do? And they'll say, change one of these parameters or add a parameter here. So input.nml is the bootstrapping Fortran name list file. And it produces, and in particular, we have these convention of using mom input and mom override. The other 2 things by convention are that the restart input and output directories are input and restart. And that will be something we saw an error earlier this morning when the restart directory did not exist. That's because we had, by convention, used restart output here is equal to restart. Highly recommend using the same convention, but you are, again, free to use whatever you want there in your own work. So that was the input.nml. So now I'm going to show you a list of the actual parameter file. And it takes this format. And unfortunately, I'm going to have to change, or I'm just going to have to stay with this format for now. Actually, you know what I might do? I'll show this in the browser. It might be a bit easier to see. So if I open a new tab here, and if I just go through to ocean only, Phillips, and then mom parameters input. So it takes this format here. The exclamation mark at the beginning of the line or anywhere in the line starts a comment on that line. And then we have these parameters in the syntax of A equals B. Is it too large? I'll make it a bit bigger. Sorry. It's extremely hard to do things with zoom overlaying things. I want to make it not too big so it doesn't wrap around on the screen. That's what I'm trying to do. So we have A equals B type syntax, you know, and then there's all these parameters, you know, on the left-hand side of the screen, and those parameters each come along with their own comments. In the input file, mom input, those comments do nothing. You can put junk here. We happen to have information here that's relevant, useful to you as a reader, but the model does not read anything in the comments. Okay, so that's just something to bear in mind. The comments are not read by the model. However, what I would like to point out is that if you look at one of the output files, I'm going to just jump to mom.parameter.short, it takes exactly the same format. And these comments have been written by the model. And so this is where you can actually get the definitive meaning of these parameters by looking at these output files. And you will get either the units, the definition, and also the default values. And we'll come back to why you need a default value if you haven't specified the parameter. And then the documentation about what, some useful comments about what these parameters actually are. For example, grid config currently is equal to Cartesian. And over here it says it's a character string. And the current options are mosaic, Cartesian, spherical, Mercator. This is about the grid. Then you have other parameters. Let's see. Let's go for this one here, jet width. The width of a zonal mean jet. This is the configurations using a jet. And the current parameter is 200, and it has units of kilometers. Okay, so these are all things which is very useful because if you assumed it was going to be units of meters, you would obviously be off by three orders of magnitude. And so having these units documented in the output file tells you what the model actually did, what it was doing with the inputs. Okay, so let me just switch back to here. So that I had to switch over to the browser just because of all the wraparound that's going on here. I want to show you one other feature about these files. There was a mom.parameter.short is what we just looked at. And that .short is the list of parameters which had non-default values, okay? In other words, it's the most concise encapsulation of what the model parameters state was, okay? And so, and we like the mom input to actually be like that, mostly, at least for the canonical version of your experiment. So if I do a diff between input and mom parameter.short, you'll see that there's only a few lines of change. Oh, actually, this is not quite what I expected. It's meant to be a lot smaller than that. I'm wondering if I'm actually out of date on this experiment. I should have done an update. The idea is that that would be a minimal of changes. And in fact, most experiments, it should just be the header, the comments at the beginning, which are, as I said, not read by the model. So if you've written comments, this is the Phillips experiment, C. Holberg 2013 at the beginning of your input file, that would be different to the generated because the first line of the generated file is, this file was written by the model. Okay, so the comments will be different at the very beginning of the file. And that's normally all you see. I apologize, I did not do an update to check that was going to work. Okay, now there are other files, and I'm doing this before I run the model just because I want, this directory is going to get populated with output in a minute. There are other files, and perhaps the most important one for you is mom.parameter.all. Now, the difference between mom.parameter.all, and I'll just show you the length of these files, is that the mom.parameter.all has all of the parameters available for this particular configuration of the model that are available. And so if I actually look at some of those, and I'll do this again in the browser. So let me go over to mom.parameter.all. Now there's going to be a lot of parameters that have, for example, apply interface filter is equal to false, and its default value is false. And that's why it didn't appear in the short, concise form of the documentation. The reason we have the .all is so it helps you find out what parameters there are available to actually turn on. But bear in mind that that .all changes depending on the configuration of the model. So for example, there might be a parameterization that is incompatible with one mode of the model, and so its output don't necessarily get written out. Sometimes we try to write them out anyway, but there are quite a few parts of the model where they're simply exclusive in terms of versions of that particular code with a configuration. And the user code is one case, is a case in point. A lot of the user code, and there's a directory source user, we'll explain this later in detail when we talk about the internals. Source users where there is configuration-specific versions of Fortran. And we reuse variables, parameters for convenience, such as the width of the domain or the size of some feature, such as the jet width, as we just saw. And the meaning of those parameters sometimes changes depending on the definition, the choice of which experiment configuration you're running. So there are quite a few cases where there are of parameters, especially these user-provided parameters, which are reused or repurposed. We've been trying, very much actively trying, Bob has been religious about this, trying to get some uniformity across all of our parameters so that we can have a single .all, but we aren't there yet. So as a word of warning, always look at the local version of your .all file to see what's available. And when you change mode, say between using the Lagrangian remap, the AL mode versus the not, so quite a few things might just change, and the new parameters may or may not appear. Okay, so that's just a caveat, some caveats about the files. And then there's just two other files worth mentioning. The layout file is about the parallelization, and the reason it's separated out is that the parallelization should not change the actual solution. Now, it might change the number of files that get written when we decompose sometimes we have our output is decomposed into parallel files or not. But the actual solution, if you recombine all your parallel files into a state and say, what does sea surface height look across the globe? That state is independent of how you parallelize. If it is dependent on how you parallelize, there's a bug. And hopefully we're not the ones who added it. And we have a session tomorrow, I think, or I forget, there's a session on processes for actually debugging. And that's one of our requirements, is that code does not change answers when you change the number of processes you use. So that's what this layout file is about. And so it's separated out because it's not relevant to the configuration of the physical part of the model, or the actual numerical solution. And then there is another file, debugging, which mom.debugging. Again, this does not change the solution, but it has an awful lot of very, very powerful parameters that we use in our debugging process. Hence, we've called this file debugging. And these are parameters which we use in our testing process, and then we'll cover a bit of this in our debugging tutorial later. So that's what those other files are. So now that we've covered all 8 of these files, remember only 4 of them are inputs. Now I'm actually going to run the model. Oh, thank you, the diag table. Yes, let's cover the diag table. Actually, no, yeah, we'll cover the diag table when we actually change the input. How about that? Okay, so I'm on a Linux environment here, so I'm just going to use MPI run, and I'm going to specify that I happen to know that I have 4 cores that I could use, so I'm just going to do that. And I'm going to use the path up to build ocean only MOM6, and I'm going to hit enter. Moment of truth. At least this is running. So, okay, so that's good. And as you can see, it's ticking away. Now, the reason I want to show you this live is there is stuff happening on the screen. This, if you're running a batch job, as you should be doing in production mode when you're doing your research, this will go into a log file somewhere that you've specified where to redirect the output to. At the beginning of this output, well, at the beginning of this output, there is a whole lot of information about the parallelization. This is generally not going to be too much use to you, other than this tells you how many points there were per subdomain that was handed to a core. So in this case, subdomains are 15 in the I direction and 20 in the J direction, X and Y. And that's a reasonable size for this experiment, it turns out. That's because this experiment is currently configured for 30 by 40, and it's been divided into 4 processes, 2 by 2, and that's why we've got 15. So that's that kind of blurb at the beginning is about the parallelization. And then the model, as it's running, is writing out some information. It's very useful for you when you're looking at this interactively and developing, just to make sure things are working. It tells you where it is in time. So mom day is currently 3.0 in this line here. But this number here is actually the time step number. So we've had 432 steps of the model. That's the outside clinic time step that Bob is going to explain in his presentation next. This is a number which is, EN stands for energy. This is either the total energy or the total kinetic energy, depending on the configuration. And it's just a number we use just to get an idea of whether things are kind of going off the scale. If this thing changes an awful lot, it's probably on the verge of blowing up. This is just a useful information. Max CFL is at that point in time, it's not aggregated over the time steps, but at that particular time step 432 is a snapshot of the advective CFL. We should, in principle, add other stability parameters in the future. I keep meaning to do this, but we keep forgetting to do it. It would be very useful to know what the time step is relative to, say, the gravity waves and so on, but they don't change throughout the evolution of the run much, whereas the flow field does change. And so plotting out the CFL is a very handy parameter to have. And as a rough rule, try not to let this get too much above 0.1. Strictly speaking, the model is stable up to 0.249 something for most setups, but you don't really want to get there. And the reason I say that is these are snapshots at a particular point of time. They're not actually aggregated throughout the full evolution. It's really like you're sampling a distribution for this. These numbers actually are varying, as you can see, they're varying from step to step, 0.1065, 0.01038, and so on. And if you were letting your CFL get right up close to the actual stability limit for one of these snapshots, because of the PDF or variability, you are likely to overstep it. As a rough rule of thumb, I like to stay at 0.1 or below. But if it's too small, as in this case, is actually too small, you're actually not running at full efficiency. This time step, it turns out, for this configuration is by default too small, and we'll actually start making changes in that in a minute. So that's the CFL number. Mass is the total mass of the model. So the model calculates how much mass or volume it has and gives you this number out. And the reason for this is that it's a very useful metric about whether we're conserving. And in fact, those numbers, the changes since the last line are actually summarized in the total energy mass line here. That's the same numbers up there, 2 lines above, but the change in that is recorded in this column here. And that change, -3, seems like a large number, but when you compare it to 4 times 10 to the 18, is actually smaller than precision on the machine. We're quite proud of the fact that we're actually able to do global budgets at higher than machine precision. That's something that we, maybe in a very detailed lecture one day, will explain how we got that. And then this error here, which is rolling off the screen, is this is the non-dimensionalization of that change, and you can see that it's smaller than 10 to the minus 2 times 10 to the minus 16i. It's better than machine precision. So we're able to do this model is running conservatively. If you were to do a budget, in principle, we're actually beating machine precision for that calculation. So that's, yes, Steve. So Steve's asking, have we thought of putting units on this? So I think we could put it in the header. We may or may not have it in the header at the top. The reason we don't is that normally this fits on a screen, and we're trying to make everything fit within the typical terminal width so that we can actually read it quickly. So we're very much into trying to, when you're developing, not have too much information. Is the information that should be there? We could put it in a header, perhaps. It would be a good idea to do that. Bob. Use the mic. You've got the mic. Yeah.
There's also a netcdf file with all the same information, and that does have all the units and a long name description of all the variables. This is kind of the shorthand version. The other one has all the details. And if those details are inadequate, it's straightforward and appropriate to add lots more details there.
Okay, so the model ran all the way to the end. And then we see this fatal error message, and that's because in our input.nml, and we saw this morning, we had said, write our restart file out in the restart directory, and I had not created it intentionally, so we see the message. So I'm going to do that so that we don't have that message. And in the meantime, and so if I ran it again, I would now get files appearing and restart file. I'll show that in a second. But since we looked at the model, this directory earlier, there's now a whole load of output. There are these .nc files that have prog, cont, and so on. And those were all controlled, most of them, sorry, not all, most of those were controlled by the Diag manager, which is an FMS package that we use for all of our diagnostic output. And it is controlled by this file, the Diag table. So the Diag table has a particular format. And in fact, I'm going to switch over to the browser, because in the browser, in the, let me just get to this presentation here. The Diag table, there is a link. So if you go to MOM6 read the docs, there is a section on the left-hand side called Working with MOM6. So this is MOM6 read the docs.io. And there's a section called Working MOM6, and there is a section called Diagnostics within that, which explains the format of the table, of the Diag table. So I'm going to use, again, I'm going to use a browser format just because it fits on the screen better. There are 3 sections to the Diag table. The first one is a sort of a label. It's just a string. It's a label for your experiment. And the next line is a date, which is the sort of reference date that's put into the time attribute in all of the model output. Those 2 are required. And then after that, there's a lot of flexibility in what you do after that. So by convention, if we're running realistic models, we use 1900, I think, as a reference date, but you can use whatever date you like. And I think we generally use model year 1, 0001 for kind of non-global models with arbitrary time units and so on. There is after that a file section. And the format of the file section is a file name. There is a frequency attribute. There is a units for that frequency. And then there is some other things to do with file format and the time access units and so on. So I'll show you what those look like in the actual file that we're using right now. So here we are. There's the file name, prog. This is going to write out output at the frequency of 10 days. There's the 10, there's the days. The units of the time axis in that file will be the units of 1 day, okay? And it will have the name time. So the time is going to be given the name time, it's going to be measured in days, and I'm going to be doing a sampling every 10 days in this file. Now, if I changed it to 5, which we'll do later, you would see that coming out every 5 days, and we could change the units to say hours or minutes or seconds. I don't know if years works, but yeah. So that section is a list of files that we are expecting to get out. Now, you'll also see that I have commented out several files here, diag, track, mom, bt, mom, so on. And we've only got the prog, the avprog, cont, and the visc files uncommented. So if I look in this directory, oh, sorry, I've already got it here. That's these files that were generated. So there's avprog, there's cont, and so on. So those are just file names which we chose, just out of habit perhaps, for this configuration. You can name these files whatever you want, but because you can just define what's in that file. So now the next section of the Diag table. Now it's a file section. The next section is the field section. And the field section has this format of module name. That's saying referring to MOM6 for the most part, but we actually have 2 main modules, which we'll come back to in a minute. Then the name of a field, and that is the name of the variable defined by the model. And then you have the opportunity to rename it. So there's an output name. So the model has, for example, the horizontal flow field components are U and V. You might want to rename it to uvel and vvel if you wanted. And so this, you would put U and uvel here in this for that component. The file name must match one of those files that you had up above, okay? And then the time sampling is I think always, actually it has to be defined as always set to all. And then reduction method is something that we're going to explain in a minute, but it can take various forms. None means just do sampling, subsampling in time. Mean or average lets you do time averages, and you can also do mins and maxes, and there's a few other operations you can do there. And then finally, there's also a few other, there's another option to do whether you're doing a regional version of the model, and also the precision with which you are writing the file out. So that's the packing option. And now if I go back to the actual Diag table, that we had here, you'll see that this section here is saying, looking at the state of U and V and H and E from the ocean model. We're going to put this into the file prog. So these variables will be in prog NC. Looking at all, unfortunately, this is using an older format. .false means none. And I had meant to update this. And again, I can look at the diag table on the browser for the updated version. This is annoying that I had made that mistake. So here's the diag table that you have if you've just cloned the model. So here it says you turn U into U, put it into the prog file. We can look at all the output, and we're going to do no averaging. And then we're going to write this out with precision 2, meaning real star 8. Now, if we go down to another section down here, this is going the same, similar line, ocean model. U is being mapped into U, but now we're putting into another file called avprog. We've put the av there because we wanted to have the time averages, and so we were doing all data, but now we're going to do a mean in time, okay? So this lets us produce a time mean of U and snapshots of U, and we're putting them in different files. Just one word of warning, you cannot mix and match means and non-means. You can't change the time averaging within a file. And you also can't change the time frequency between files. So each file is basically demarked by how you're handling time, both in frequency and in processing, whether you're doing averaging or not. Okay, so that is the diag table in a nutshell. And we have a lot of the time at the bottom of the file actually got a quick summary or in the comments. The hash in this file, the hash is the comment symbol in this file. And we've got a quick summary of that by convention, but that's not a requirement. But it's kind of good practice to take an existing diag table with the newer format and with these comments, and then use that so that you can quickly refer to the bottom of the file rather than trying to find that read the docs page with the revision up, because as you know, that the URL is longer than you can remember. Okay, so how are we doing on time? I'm actually only got 5 minutes left, right? Yeah. Okay, so I want to just quickly go into MOM override. So we just ran the model, and you saw this output appear, but I showed you that the CFL was actually short. Now, there's one file we didn't go into, and that's the override file. So by default, we provide a blank override file, and this file is nevertheless included in the list of parameters. And the reason for that is that it's very useful when you are running experiments and developing experiments to be able to separate out the canonical version, which we think of as being defined by MOM input, and perturbations on that experiment, which we think you should put into a separate file, and MOM override is how we're doing it. We call it MOM override because if I was to do something such as specify a variable, dt is the parameter I would like to change. So I'm going to set this to 3600 seconds. And I try running the model. It's going to give me a fatal error. And the fatal error is that we have specified dt twice. We specified it in MOM input. So let me just find dt from MOM input. So there it is. It's specified at 600 in MOM input, and we just specified 3600. So the way we get around that is we have an approach where you can specify a parameter, and you can indicate that you mean it to be an override. So you put a hash override in front of dt, and now it will run, or it should run. Okay. Now, one reason that we like to preserve the doc.all files in our experiments is, I'll show you this in a moment, and this is going to run. Remember, I created the restart direction, so this will end cleanly. Fingers crossed. Oh, by the way, remember that in day 3 we were at step 432. So now we just increased the time step, and so now step 432 actually was day 18. You see, so this is now running faster. Our CFL numbers are larger now. 0.05 is not too bad a level. And at the end of the model, we actually get a summary of what we call the tail sheet, the timings, and these can be provided more finer grain if you want. But generally, we have coarse grained. How long did the model take to run the initialization and the main loops? And so this model ran 24 aggregate seconds, even though it only took about 4 seconds, 6 seconds or 8 seconds wall time, because I'm using 4 cores. Okay. Now, if I do a git diff just to show you what changed in the short output file, short document file, you'll see that we have indeed ran the model with the time step of 3600. Okay. So that was running the model with a different time step. So that ability to provide overrides two parameters, so you can kind of separate out your perturbation experiments from a canonical experiment is, we think, a very I mean, this is an extremely powerful way to manage your own work, is to keep concise changes, deltas to the model in this way. Okay, so there's one last thing I want to do is we're going to run the model long enough that RAF has some output. So we're going to change the length of the run. So I'm going to do another override. And you can follow me if you can. How many was it? 100 days? 100 days? So day max is measured in days. That's something specified in the input. And I'm also going to do one other thing. We're going to turn off two other parameters, because I told you this was based on a paper by Hallberg in 2013. And in that model, the whole point of that was to try and actually make a parameterized model match parameterization of measure scales actually work regionally within the channel. And we're going to turn off the parameterization by setting KHTH equal to 0. And I'm also going to turn off something that's doing something very clever, which was the whole point of that paper. If you want to try, oh goodness me, it's beautiful on my screen. I totally agree. Yeah, I can't really do much about that. I don't know how to. How about if I do this? Please remember to put a hash in front of override. So if you put hash in front of the override, I'm changing 4 parameters here. I'm setting DT to 1 hour, 3600 seconds. I'm changing day max to 100, so we're going to run the model for 100 days. KHTH, I'm setting to 0 because it had a non-zero value in the MOM input, even though its default value is 0. And then this parameter here, oh, I've got to make sure I get the case right. Do not have, all of our parameters are uppercase. Resolution scaled KH. This is the whole point of the Hallberg paper was to try and modulate diffusivity and viscosity parameters. And that was turning it on, and I'm setting this to false, not to 0. It's illogical. And we would have gotten an error if we tried running that. Okay, so can I now turn this back to blue and actually try running it, please? Because we're running out of time. So I'm just going to run that. So that's going to run. So it'll take a little bit longer than last time. So if you're on a Unix laptop, you should be using MPI run. Oh, I've just stopped it. MPI run minus n, the number of cores, and then the ... path to the executable. So this is the same one which was used to run the double gyre experiment. Yeah, you just used one processor. I'm running 4 here because I'm trying to make this go fast enough that we can get to the end of this, which I'm basically done. So in fact, we don't need to watch this running. The whole point was to get to this point. I've explained what the inputs are. I've explained that there's some output files, but RAF is going to actually do the analysis on that output file, and it's 100 days. I would provide the output. There's a failsafe. Yeah. Okay. So yeah, I totally agree. So if you could, okay, we'll have a look at that. Has anyone else managed everyone else managed to at least follow or try something? I mean, you can just run the original configuration first, and then if you use this override syntax, you should be able to just do those 4 changes. And that is it. So I'm going to leave it running here so that I have it on my laptop, and we're done. That's all we wanted to do, is show you what the model does when it's reading, how it's looking when it's writing out. And Raf is going to show you some of the output when we in this afternoon, right? Okay, so thank you. Next up is